Thank you, Bruce. Can you see my slide?
Yes.
Yeah, Bruce, thank you again. And I would like to also thank the Sustainable Horizon Journal for providing the platform. I'm very grateful for the opportunity to share the platform with distinguished Professor Jingwo Won, Professor David Wei, and Professor Xiaobing Wang. They are the giants of the field, and it's such an honor to be able to follow their footsteps. And today I'm going to talk to you about my work, or it's actually our work, because there are a lot of people behind this work, focusing on uh, a microalgae-based platform for carbon capture. And you will see we focus specifically on a separation process to lower the cost of microalgae harvesting. I will touch base on a few other challenges in converting microalgae into a carbon capture platform. But the focus is very much on harvesting. So the previous talks have already mentioned the global challenge of climate change. We need some very urgent action, and biocarbon capture technology is very much needed. We have done some trials around carbon capture and storage, try to use chemical processes to capture carbon dioxide and then pump it into an underground aquifer. But so far, most of the pilot projects have returned negative results, meaning that they are not actually delivering the objective of sequestering and capturing the carbon, and therefore we need to have an alternative. Of course, we can grow trees, but it's a very slow growing platform compared to zit litter species. And you probably recognize what it is microalgae. An individual microalgae cell multiply very fast. This video have been fast forward by 600 times. But basically, every 5 hours, the microalgae cell will double. That really means over 10 hours, it multiplied by 4, and then over 15 hours, it multiplied by 8. Mathematically, you can quickly work out that that over 2 days, it will multiply by 1,000 times, which is a huge number. And if we can utilize that, then we can truly have a platform that is scalable and cost-effective enough to capture carbon from the atmosphere. Now that mathematically straightforward, but in reality, it's not very simple. There are a few challenges that we need to address when we look at microalgae as a platform for carbon capture. I outline those challenges first, but then I will also touch base on some of the strength that the platform will give us. The first challenge is the very space intensity requirement for cultivating microalgae. So the traditional technique to cultivate microalgae, we need thousands and thousands or even millions of hectares if we want to capture carbon at a realistic scale. And that is because while it is growing very fast, microalgae only grow at the very surface of the cultivation area, where it need to get sunlight, and then carbon dioxide from the atmosphere. It can also be from flue gas, and then a bit of nutrient to grow. Now, once we can grow the microalgae, there's another challenge. That is, at maturity, the solution have a very low biomass content, usually 1 gram per liter or 1 kilogram per cubic meter. That work out to be roughly about 0.1% of biomass. Now, that is a lot of water and a tiny bit of microalgae. So the next step for us to convert that into an industrial process is to get the microalgae biomass. The waste microalgae biomass is about 10 to 20%, and we need to get that before we can do anything meaningful. Once we can get that, then obviously the next step is to utilize the microalgae biomass to convert that into things like bioplastic, biofuel, or animal feed. A lot of things that we can do, but it will involve in some chemical processing, and it can be quite expensive. So overall, we have a few challenges, and we need to basically develop technology to lower the cost and address those three challenges. Nevertheless, if we look back at microalgae as the platform for carbon capture, it can be very simple and very effective because it doesn't need a lot. It does need to have some water, some nutrient, and it will grow by taking up carbon dioxide and sunlight as the energy input. Now we can replace sunlight with natural light or LED that give us a good platform to address the problem of cultivation. So another slide that shows very much the same thing, and work that we have done at my University of Technology Sydney, have very much addressed all three challenges that I have just mentioned. We have recently patented a process, or I should say a design, in which we create multi-layers that is possible for light to penetrate into multi-layers within a defined space, so that we can significantly intensify the cultivation of microalgae. We have also looked at genetic selection to select elite strains of microalgae, flickering, so that we can reduce the energy input into the photobioreactor, and we can also regulate the wavelength of the LED to optimize the wavelength and therefore reduce the energy input. So altogether, we have been able to demonstrate at lab scale and to some extent at pilot scale a massive reduction in the required space for microalgae cultivation, as well as energy reduction as well. We have done similar thing in the area of product recovery, but today with limited time, I like to focus very much on harvesting because it is also very much aligned with the expertise of the audience today. Harvesting currently accounts for about 30% of the production cost. As I mentioned before, that is because we have to separate a large volume of water from a small amount of microalgae biomass for subsequent utilization. So we have looked at a large number of microalgae species. So you can see here the microalgae bank that we have at UTS. And the next few slides, I'm going to focus exclusively on how do we improve the harvesting efficiency. Now we set up a very simple approach, that is, in order to lower the cost of harvesting, we need to do two things. First of all, we need to move away from the traditional but very energy intensive technology, which is centrifugation. So centrifugation worked very well, but it had been very energy intensive and then for costly. It's only suitable when we produce microalgae for cosmetic, for the cosmetic industry or for high value products. Now, number two, I keep repeating myself that the mature microalgae solution have a very low biomass content. So we will need to pre-concentrate the biomass concentration before we do the harvesting. So we come up with a very simple approach, and our approach is basically to pre-concentrate the microalgae using membrane filtration. In this case, we would use ceramic membrane. And it is only a pre-concentration. The membrane is not for harvesting. I need to emphasize that the membrane is only to enrich the microalgae concentration, but not for harvesting. And then we look at the second step, which is to use polymeric flocculation as a harvesting method. And I would also talk a bit about our scaling up method that following what David have shown people today is very important to make sure that we get out of the lab and work at a pilot scale level. So I'd like to first talk a bit about our work on using membrane to pre-concentrate microalgae. So in this case, I use a ceramic membrane. This is a aluminum oxide membrane, flat sheet membrane, of course, submerged. So it's very suitable for scaling up later on. And when we use a membrane to pre-concentrate the microalgae solution, as you can expect, it works quite all right. It can concentrate the microalgae solution to a factor 4 times, or we can achieve 40% water recovery. However, as expected, you will see a decrease in the transmembrane pressure, which is the you can see that the transmembrane pressure is a black sorry, I need to do it again. It's a black symbol here. Let me change the color. The black setup symbol here. You see the increase in transmembrane pressure for 2 different microalgae species, Chlorella vulgaris and Selendemus. So you can see that Chlorella vulgaris, the transmembrane pressure increase is a lot faster than Selendemus. You see 2 trajectory here. That is because we were operating at 2 different recovery rate. But overall, you can see that we can achieve 80%. Now, the flux also decline, even though we operate at a fixed, a constant flux, but because the transmembrane pressure increase is too much, you can see a significant flux decline for the case of Chlorella vulgaris, where the flux decline is actually quite constant or a lot less for the Selendemus. So, okay, we accept that when we pre-concentrate the solution, there will be flux decline. But of course, we can regenerate the membrane by backwashing. So let me show you how effective it is when we do a simple backwashing. Okay. Right, so when we backwash, basically with the reversal flow, you can see that the microalgae deposition on the membrane surface get completely removed, or I should say mostly removed. When we do it over a repetitive cycle, you can see that we can most of the time recover most of the flux. But if we do it over 10 cycles, we can start seeing some foulant residue on the membrane surface. So, and the residue of foulant on the membrane surface is also species dependent. With Chlorella vulgaris, it's very little, but with Selendemus, is quite obvious, and that can be explained by the morphology of the microalgae itself. So Selendemus is a very interesting green microalgae. Number one, it actually occur in the environment as a pack of 4 cells attached to each other, and it also have a whisker, and it have a very muscular membrane cell. And we attribute the residue on the membrane surface to that very muscular membrane cell. That means over the time, the flux will decline, and then we would have to undertake chemical cleaning. So we accept that, but it's obviously also good to see that ceramic membrane can have to pre-concentrate as long as we have an effective membrane cleaning later on. So let's look at how we can do membrane cleaning in this case. So what we have done is we then switch gear. We look at how do we can coat a zinc oxide layer onto the membrane. This is that a fundamental study. So instead of using a large submerged membrane, we have to use a small membrane sample. So I should note that the membrane sample we use in this part is only 1 centimeter square. That would allow us to effectively in the lab deposit zinc oxide onto the membrane surface. So what we have done is we deposit zinc onto the membranes, zinc oxide onto the membrane surface. Actually, we have two techniques to develop the zinc oxide on the membrane surface. Technique number one, we deposit zinc oxide directly onto the membrane surface. And technique number two, we first deposit zinc metal on the membrane surface, and then we oxidize at 800 degrees centigrade to convert zinc metal into zinc oxide. So we also end up with a zinc oxide on the membrane surface. Now that zinc oxide would have photocatalytic property, as I will show you later on when I'll show you data of the membrane characterization. And with that photocatalytic property, basically when we shine a UV light onto the membrane surface, we can then initiate the photocatalytic function, and then it become a cell-cleansing process, which is very effective to do the membrane cleaning that address the problem that I mentioned earlier on, that there's some residual fouling on the membrane. So we have demonstrated that recently. So we filter the membrane. We use the membrane to filter microalgae solution. In this case, we use the species that cause the most problem, which is Salendamus. And then we rinse it, and then we radiate with UV to check the flux recovery. But let me show you our data regarding the characterization of the zinc oxide coated membrane. As I mentioned to you before, we have two different techniques. One is to coat zinc oxide directly onto the membrane surface, and you can see the SEM image here. The substrate we use is a stainless steel. It's a porous stainless steel with very large pore size of about 10 micron, because the microalgae is large enough, and 10 micron pore size is more than enough to retain the microalgae. I should note, and I didn't show you the data, but I can provide you with information that the retention or the rejection of microalgae in our case is only 99% plus. So it's very effective, even at the large pore size. And when we coat the membrane with zinc oxide, you see that the membrane pore size doesn't change because our coating layer is very thin. And indeed, you can see here that for zinc oxide coating, we have a layer of about 820 nanometer. And when we first coat zinc metal and then oxidize into zinc oxide, we have a layer of about 120 nanometers. So it's very, very thin and small compared to the pore size of the membrane. I beg your pardon. I just need to say something. I apologize, I'm back now. So this diagram shows us the elementary composition of the membrane surface after we have coated it with zinc oxide, and it's very evident here that we see zinc all over the place, which is good. With zinc oxide coating, I mentioned before that we have a slightly thicker layer, and therefore the peak is stronger compared to the case when we coat it with zinc and then oxidize into zinc oxide. And when we look at the substrate, which is stainless steel, we only see the material in stainless steel, which is nickel and iron. When we check the transparent of the zinc oxide film, so basically what we have done is we put a glass layer into the coating chamber. So the zinc oxide also coat the glass layer, and then we remove that coating layer so that we can check the optical property of the coating layer. And you can see that the coating layer is very much transparent to the UV range with a very sharp absorption edge at around 380 nanometer. This shows very good photocatalytic property. And the torch plot also show that our coating layer have a band gap of about 3.2 EV, which is really good for photocatalytic property. So let me show you also the contact angle or the hydrophobicity of the membrane. After coating, the membrane become hydrophilic, and because it is more hydrophilic, you can see that the permeability of the membrane actually increased compared to the base stainless steel membrane. So this is good news. This is probably the most important part of our study. After coating, we filter the microalgae solution, achieve 90% recovery, and then we do the self-cleansing. We can see that with the zinc oxide coating, after we radiate it with UV, the flux recovery was significantly higher than when we only rinse the membrane without UV radiation, and we can recover about 60% of the initial flux. Now, 60% of the initial flux is not very high, and this is only the beginning of our work. Nevertheless, we have effectively shown that there is some self-cleansing property. Now, we do need to bring that 60% flux recovery to 100% flux recovery, and it is ongoing. We're going to increase the UV strength, and we will also optimize the coating layer. Nevertheless, this preliminary result is encouraging. It shows that we can effectively develop a platform for self-cleansing. So let me now switch over and quickly talk to you about our next step. One, we have pre-concentrate the microalgae solution. We can then look at recovering the microalgal biomass. So we look at a number of techniques that are available, and obviously flocculation is the most simple and effective technique for large-scale operation. We then check a number of different coagulants, inorganic coagulants as well as organic coagulants, and we see a very clear picture that have emerged. Inorganic coagulant is not very effective, and polymeric coagulant itself is also not effective unless it is cationic and highly charged. And that is because in order to effectively flocculate the membrane, we need two things. We need to neutralize the negative charge of the microalgae, and we need to have a polymer that is of sufficient molecular weight so that it acts like a spider web to capture all the microalgae individual cell and aggregate it. Then we see that there is a commercial product, which is the FO 4808, that can be very effective. And if we use it, cationic polymer, we can achieve 99% harvesting, very fast recovery, and the overall cost of production is actually quite low. We work out that it's only about $120 per ton of microalgae biomass that we can harvest. But we need to look further into it because we see sign of cell damage, membrane cell damage when we do the harvesting. And in fact, it is very well known, even with centrifugation, we will also have cell damage. So we use a technique called we use a technique called gas chromatography mass spectrometer to check for the individual chemicals inside the microalgae cell after harvesting. And the result is quite encouraging. Of the three different techniques that we use for harvesting, namely centrifugation and inorganic chemical and polymer flocculation, we see that polymer flocculation results in the microalgae biomass, usually with the highest concentration of the organic content. Here we are looking at amino acid, fatty acid, organic acid, and sugar content. Whereas with centrifugation, there's a significant loss of cell content. Now this is, by the way, unpublished data. We haven't actually finalized the publication yet. So this is good, this is encouraging. We also observe that we usually achieve the best harvesting efficiency when the microalgae is at the mature stage. Now, let me just explain a little bit here. When we cultivate a batch of microalgae, it will go through three stages. First, it called the early exponential stage. So it grow up slightly, and then it go into the exponential stage where the multiplication rate or the growth rate is very high. And then usually after about 2 or 3 weeks, it reaches a stationary growth rate. That is at maturity, and we cannot increase the biomass concentration or the biomass content in the solution anymore. That is at stationary stage. And we realize the data we have here with 3 different microalgae show that we always have the highest harvesting efficiency at the mature stage or the stationary stage. Before I move on, I want to also quickly show you a set of data that is also important for us. That is the ability to recycle the water after we have recovered the microalgae biomass. In this case, again, we're looking at 3 different microalgae species. And repeatedly, 3 times, we have always been able to grow another batch of microalgae with the water that we have after harvesting. So we can fully recycle the water, which is very important when we need to grow microalgae in the desert, which is basically the ultimate objective. We don't want to grow microalgae on arable land. We want to grow it where space is not useful for any other purposes. So let me go back to the question of why is it we see the highest harvesting efficiency at the mature growth rate or stationary growth rate. We have a few hypotheses. Number one, as the microalgae grow, there is some changes in cell morphology, shape, and size, and the surface charge of the microalgae cell will also change. And as the as microalgae grow, it consumes phosphorus, and therefore the concentration of phosphate in the solution will decrease. There have been some previous work in the literature that show that phosphorus might impact on the flocculation efficiency. and we want to check all of that. So we carry out a set of experiment where we take the sample from a 350 liter microalgae reactor, and we take it at 3 different stages. The early exponential, the less exponential, and the stationary stage, and we do the harvesting. With regard to the surface charge of the microalgae cell, you can see here in the blue set of data here, the microalgae surface charge become more negative as the solution mature. And obviously, if you look at the biomass content, you can see that the biomass content of the solution increased until it's basically stationary phase. So clearly, there is some impact from the surface charge of the membrane of the microalgae cell. However, if we look at the microalgae shell after flocculation, you see that it doesn't need to go back to zero in order to have complete charge neutralization, and we can still get very, very high efficiency. So yeah, charge is an impact, but probably not a very high significant factor. When we look at phosphorus residue, what we have done is we add a tiny bit of phosphorus so that we can change the phosphorus content at the end, and we didn't see any impact of phosphorus residue on harvesting efficiency. So we can very much cross out phosphorus. And when we look at the morphology of the microalgae cell, I think that it probably be the main reason why at stationary stage, we always have the highest harvesting efficiency. You can see that as the microalgae grow, the content of soluble carbohydrate and soluble protein also increase. So is the bioprotein. That means the microalgae cell become carb-like, a bit hairy with extra cellular polymer outside of the cell, and that would interact very well with the polymer that we use for harvesting, and that probably be the main reason why we see very effective. So overall, when we look at some fundamental question as how we can optimize the flocculation by polymer for microalgae harvesting, we can see clearly that basically it's a rather simple process. We need to have a sufficient molecular weight so that the polymer can act like a spider web, but it needs to be sticky. So we need to have a highly positively charged polymer so that we can, at the end we have a very sticky spider web that can aggregate on the individual cell. By the way, in the image, what I show you is the microalgae shell after polymer flocculation. You can see that under the microscope, they come very close. They come together as aggregate, and then on this carb-like figure, you can see the microalgae cell. They stay in isolation because we haven't added any polymer, and therefore they will always repel each other by charge repulsion because they are negatively charged. So armed with that knowledge, we have now successfully developed a polymer, and our polymer is actually very effective by adding a tiny bit of our polymer. You can see in this video that a tiny bit of polymer can allow the microalgae solution to aggregate in no time. And once it aggregate, we can then separate and recover the microalgae aggregate using any sedimentation or flotation device. So in this case, we have set up a pilot system where we add polymer into the microalgae solution. You flotation, and then your conveyor belt to then move it outside of the water solution. So how do we make the polymer? We basically use photo-initiated polymerization process. So in the system, we have a photo initiator and a monomer. And when we radiate the solution of monomer with the photo initiator, we trigger the reaction chain of polymerization, and then we can then form the polymer. Now, the beauty of this simple process is the fact that we can then regulate the molecular weight and the charge density of the polymer by controlling the monomer concentration as well as the UV power. So we have tested the method with two polymer called PTEC and PAMTEC, and then we contrast our polymer with commercially available polymer. And you see that our polymer, they are on the top figure highlighted in blue here, have much higher harvesting efficiency, or in the case of the other species, red microalgae, our polymer have the same harvesting efficiency, but require a much lower dose. So in this case, the PTEC only require about 5 milligram per gram of biomass. So this is really, really low dose. And we have recently obtained some proof of concept data to show that by changing the molecular weight, we can change by changing the monomer concentration, we can change the polymer molecular weight at the end. And likewise, when we change the monomer concentration, we can also change the zeta potential or the surface charge or the surface density of the polymer to some extent. We have also we have also got some preliminary data to show that same thing can be done by changing the UV strength. So I just want to quickly put everything together. I have only showed you our work in harvesting, but I have also mentioned to you work in the other area and cultivation. Ultimately, what we wish and we want to do is to be able to produce modular system. We call it Green Genie, and Green Genie will be solar power, and it will detect sunlight, CO2 from the atmosphere or flue gas, and the nutrient from wastewater, and produce microalgal biomass. And the ultimate aim that we want is to produce algal biomass at the price of $1 per kilogram. And at that price, we believe that it will be commercially viable to scale it up to a gigaton production capacity. And when we can produce a gigaton of microalgal biomass, that later on can be the feedstock for petrol, for the chemical industry, for animal feed, for biofuel, we'll be able to capture a lot of CO2. We have converted our system into a pilot scale. We now have a portfolio of patents, and we demonstrate our system in containerized, and we have opened it recently, and it was visited by the Federal Minister for the Environment in Australia. So I think my time is up. I just want to recap that it is possible, and we believe that we can develop a microalgae-based platform for carbon capture. We have gone a fair bit with the effort to reduce the cost of harvesting. That is one critical aspect of to scale up microalgae-based carbon capture. And that can be done through first pre-concentrate using membrane, and then harvest the pre-concentrated microalgae using polymer flocculation. And we have also demonstrated our concept at pilot scale, and a few weeks ago, we have now formed a spin-out company to take the work further. So very soon, this work will be packaged and commercialized, and will much of that will be out of the university and into the commercial world. And with that, I'd like to thank you for the attention, and once again, thank to the Sustainable Horizon Journal for the very useful seminar. Thank you.